Hello. Today we go over tautomerization, specifically keto-enol tautomerization. And so keto simply refers to we have a ketone. So let's say we have this R group, and let's say R prime group to distinguish them, although it doesn't matter for this example. And I'm going to draw these two as placeholders for the equilibrium for now. Although the positioning of them might give away what we're going to talk about. We're going to talk about which one is favored and why. And so here we have, sorry, this is the enol with the double bond here. Here we have a double bond between a carbon and an oxygen. Here we have a double bond between a carbon and a carbon. In the carbon-oxygen bond, double bond, we have electron density being pulled towards the oxygen due to oxygen's electronegativity. And so here we have a more polar bond, which is going to be shorter, and because it is shorter, it is going to have a higher, it's going to require higher energy to break it. So this is going to be more stable, or contribute to this molecule being more stable than this molecule, and just because of thermodynamics. So this one, the keto form, will be highly favored in keto-enol tautomerization. And so let's draw the mechanism out for how the enol form will form the keto form. We'll draw it down here. We have the enol form. And let's say we have an acid. We'll say we have hydronium. And let's say this is because it's in water, or there's water nearby, and water is always in equilibrium with hydronium and hydroxyl. So here we have a oxygen with a positive formal charge, and we also have, let's say, let's put these electrons. We also have, sorry, we draw a bit bigger so it's visible. We also have this double bond, which can act as a nucleophile and attack as hydrogen, versus push down these electrons so that this can attack as hydrogen, and this bond will, between the hydrogen and oxygen from the hydronium, will then go to the oxygen for the electrons in here, will go to the oxygen, which will form water, and that will stabilize the hydronium. And of course we have this going down here because of we're trying to prevent a carbocation from forming here. And so now we have, and let's just say, I'm not showing the relative favoritism, I suppose, between steps. I'm just going to use this because it's a proton transfer, so it's interchangeable. It's you can go forward and back. So yeah, then we have this molecule where we have an oxygen that's been double bonded to carbon, and it's single bonded to a hydrogen. And we also have water, which is formed down there. So let's get that water over here. Make sure to show the lone pair electrons. This stuff. And so we have, again, we have the oxygen, which has a positive formal charge, and but that obviously this oxygen now. And we want to get rid of this hydrogen. Well, what can we do? What do we do up here? Or I suppose it's a bit different now, but we can use these lone pair electrons from this oxygen, can attack that hydrogen, and that will result in the electrons from this bond going back to this oxygen, which will then result in the keto form. And voila, we've shown keto-enol tautomerization. This is a very important mechanism to know. Let me just make sure it's in frame. Yeah, it's in frame. Because it happens a lot in biology, it happens a lot in organic chemistry. If you have the enol form, you can very quickly have the keto form. And so if you're doing synthesis in organic chemistry, if you're doing a mechanism in organic chemistry, and you're trying to see how you get from one step to another, then, and if you can form an enol and you want to get to the keto form, then, well, just form an enol and say, well, through keto-enol tautomerization, we then have this form. And then you can move on with your synthesis, you can move on with your mechanism. We're going to go over in keto-enol tautomerization. And of course, this is when there is equilibrium between the keto form, which is this one, and the enol form of a molecule. Oh, wait, that's wrong, sorry. And so yeah, here we have the enol form and the keto form. And here we have the equilibrium arrows, which I've not drawn the pointing direction to yet, although it might be obvious since this is in the location. But we're going to go over why one of them is favored. And we're going to look at the bonds. So we have a carbon double bond to an oxygen in the keto form, and we have a carbon double bond to a carbon in the enol form. And so we know that there is going to be a lot of withdrawal of the electrons towards the oxygen by the oxygen because of its electronegativity. And of course that will form a shorter bond. And we know that shorter bonds are, they require more energy to be broken. And so when you have a carbon double bond to an oxygen, it is more stable, more thermodynamically stable than a carbon double bond to a carbon. And so for that reason, this is going to be preferred, which means that when comparing these two molecules, which the only difference is the enol form here versus the keto form here, the keto form is going to be heavily favored. And let's draw the mechanism of keto-enol tautomerization to indicate how the enol form can result in the keto form. And so we're going to have the enol here. And let's say that there's water in the environment, and because there's water, that also means that there's hydronium and hydroxide ions because of the fact that water, hydronium, and hydroxide are all in equilibrium. And so we have a hydronium ion here. And we have these lone pair electrons from the oxygen. So let's say that we want to stabilize this hydronium ion by converting it to water. That would mean that we would use this double bond to attack that hydrogen. But also we would need to push down the electrons from this oxygen down here to prevent the formation of the carbon cation in that carbon. And since we're attacking this hydrogen down here, that would mean that these electrons would be going to the oxygen and the hydronium, ultimately forming water. And so let's draw out what what this results in. And I'm not indicating any favoritism or any favoritism in which direction this would go in the mechanism, because we already know that obviously the keto form would be preferred, as mentioned earlier. And so we have these two molecules now. We have water. Oh wait, hold on. We have water, and we have here we have the oxygen double bond to a carbon, and as well as to a hydrogen. But we also have water, so let's draw out the water here. And so we have water, we have this molecule, but now this oxygen is very unhappy, we can say. And similar to before, we want to get this this bond, in this case this bond, to go towards the oxygen, the electrons in that bond to go to the oxygen to stabilize the oxygen. And how can we do that? Well, we can attack this hydrogen with the lone pair electrons from the oxygen, and that will result in the electrons from that bond going to the oxygen, as happened down here. And so now we have hydronium, but we also have the keto form. So we have hydronium and the keto form.
And now, of course, since this is a proton transfer, you can go backwards and then go all the way to the enol form again. But of course, as we explained earlier, that is heavily disfavored. So in a we will see this molecule much more so than the enol form. And so yeah, that's the mechanism. It is I would say, an important mechanism to know because many times in organic chemistry as well as in biology, if you have some sort of enol, you should know that the keto form will form very rapidly. And so if you're making a synthesis where you want to ultimately form the keto form, but you can form the enol form very easily, for example, then, well, just form the enol form and then you can form the keto form afterwards by just saying that the tautomerization occurs. Likewise, in biology, if you see an enol form in some molecule, then just know that it might turn into the keto form, or it will likely turn into the keto form, and you should be knowledgeable about that when looking at a biological molecule. And so yeah, that's it for the mechanism and for the reasoning for which there is a difference in the equilibrium in terms of which one is favored. I'm sure I potentially missed something. Please comment with anything I missed or any more information that's necessary or that you think is necessary. Yeah, that's it. Thank you.